Oh, did I? I think I was trying to remember if I fixed the focal length on it. I think I did. Is it zoomed in? Yeah. I'll begin with a word of prayer. So, Dear Father, we thank you for this day. I thank you for students. Just ask you to bless this class today, Lord. In your name I pray. Amen. So I thought I would share this calculation with you as quickly as I can. Maybe not all the details, but just enough so you can see how I would do it. So I realized that in the hyperbolic plane, so here, h is what? X plus jy, such that x and y are real numbers, and j squared is equal to 1, right? So we have learned before that the zero divisors of the hyperbolic numbers have the form, x plus jy, such that y is equal to plus or minus x, right? So I have drawn those zero divisors as dotted lines there. And so if I'm thinking about the question of, what would it mean to integrate around a unit circle, if anything, in the hyperbolic plane? So I thought, well, one possibly useful interpretation of that integral might be to sort of generalize the notion of an improper integral or the principal value calculation to consider approaching the singularities in the circle in a symmetric way. So, basically I'm thinking of just excluding these points, right? So maybe this is, how to say this? So I actually broke it up into 4 arcs. So here's theta equals to 0, theta equals to pi over 2, theta equals to pi, theta equals to 3 pi over 2. And what I did was just to look at each one of those quarter circles with that interior singularity in sort of the natural way, in the sense that I'm going this way. Well, let me just focus in on the red one. And all right, so generically speaking, any of these integrals that I'm talking about, they all basically center around the problem of how do you parameterize the unit circle, right? And what's this integral look like? So I'm going to do it over here, just sort of generically. We have z equals to what? It's a unit circle. So I'm assuming c is, x squared, x plus jy, such that x squared plus y squared equals to 1, counterclockwise oriented, right? So to parameterize that curve, we can just use z equals to cosine t plus j sine t. That is the usual parameterization of the unit circle. It still makes sense here. And, but then when you look at what's dz dt? Well, dz dt is minus sine t plus j cosine t. And then so to calculate the integral of dz over z, it's something like integrating 1 over cosine t plus j sine t, right, that times minus sine t plus j cosine t dt. This is and of course over the appropriate parameter domain. I'm being a little bit sloppy here for just a moment. Maybe I should forget about the integral and just say that, forget about the integral here for a second and just say that what I'm looking at is 1 over, z of t times dz dt, which is the thing you're going to want to integrate with respect to time to actually do these integrals over here, right? So simplifying that, you simplify this by doing cosine t minus j sine t divided by cosine squared t minus sine squared t, and that times minus sine t plus j cosine t. And how does that work out? Well, that gives you a minus twice sine t cosine t because I get 1 from this times that, and then j squared is 1, so I get 2 copies of sine cosine, both minus. So I get minus 2 sine t cosine t. And then I got a, what else do I have here? With the j terms, I've got j minus j sine squared times minus, I've got a j sine squared, and I've got a j cosine squared, so sine squared plus cosine squared is 1, so I just get plus j. And downstairs, cosine squared minus sine squared, well, fine, I'll write it like that. Cosine squared t minus sine squared t. But of course, this simplifies, right? Because we know trigonometry, we know that what we're looking at is minus the sine of 2t plus j divided by the cosine of 2t. Which then simplifies further to minus the tangent of 2t plus j the secant of 2t. And so what I did was then to give that thing a name, just to let's call it g of t. And so to calculate this integral, what I really want to do is to say integrate from 0 to pi over 2 g of t dt plus the integral from pi over 2 to pi of g of t dt plus the integral from pi to 3 pi over 2 g of t dt plus the integral 3 pi over 2 to 2 pi g of t dt, where each one of those integrals I'm viewing as an improper integral, where the improper event happens right in this smack dab in the middle of their integration domain. So I can approach it symmetrically in a limiting process. Like, here's what I mean. This is a heuristic notation for the red piece. In particular, what I mean by that is actually the limit as b goes to pi over 4 from the left of the integral from 0 to b of g of t dt plus the integral. And here's where I had to think a little bit. See, to approach it symmetrically, I need to be approaching from the one side and the other side of the divergence in the same way, right? So I need to use a single limit to approach both sides. That's what I'm trying to capture. I know that if I approach the sides independently, it just blows up. I get independent infinities, which don't cancel, because we don't cancel independent infinities, because we're not physicists. All right? So what do you got? So I need to make that I need to approach pi over 2 from the right, as opposed to from the, you got pi over 2, right? We got b going like that, right? So that's a left limit, pi over 4 rather. So I'm trying to go the other way to approach from the other side, yeah? So what should I put as the lower limit? Yeah.
I might have missed this, but why are we going from 0 to pi over 2 instead of pi over 4 to 3 pi over 4? Why do we go over the spot where it's that instead of going between them?
I think it's equivalent as long as we do all of them.
Did you guys go between them rather than over them and also get 0?
I just did all of it.
All of them at the same time? That's fine with me. Hey, this is up for grabs. This is the wild west of mathematics here. There's no definition. We're proposing a meaning for the integral and seeing if we can calculate something that's possible. So I'm happy to look at your solution that is based on a different setup to this. That's great. Actually, that's helpful to me to have another way of approaching it. So this is not written in stone or anything like that. This is just.
Oh, I haven't done it. I was just wondering.
Oh.
That seems.
I think Sam has done it the way you're describing it.
Well, no, I think I'm not entirely sure, because what she's saying is are you doing you take these 4
Well,
quadrants?
let me,
add them up?
this is pi, yes, pi over 2 minus b, first of all.
Because what I did is I did it all the time, all the limits at the same time, so I didn't have any like sublimits and then add them up. So I feel like if you take sublimits and add them up, it might matter where you do it, but I don't remember the details.
I think there are many questions like that which are open here. I'm not sure. If I did it differently, would I get a different result? Yeah, I don't know yet. But if I break it, if I'm approaching this interior singularity in a symmetric way, that means I have to pick a symmetric domain, a symmetric interval about it in order for this limit, this paired limit to make sense. And but you see, if I do pi over 2 minus b like that, then that means I'm approaching this side with pi over 2 minus b, right? If I approach pi over 4 like that with b, then pi over 2 minus b approaches pi over 4 from the right, right? It's a plus limit, essentially. And so, again, same integrand. And so, by the way, the antiderivative of this, here it is, it's minus 1/2 the natural log of the cosine of 2t. But there's no minus because the u equals cosine substitution brings out a minus. So that eats the minus. And then the integral of secant, of course, is 1/2 secant plus tangent. And the half because of the u equals 2t substitution. So that's an antiderivative for g of t. And the pretty cool thing is, if you look at, so long story short, g of 0 and g of pi over 2, what are they? If you plug in g of 0, you've got 1/2 natural log of the cosine of 0, which is natural log of 1. You've got the natural log of the secant of 0, which is 1, plus the tangent of 0, which is 0, which is again a log of 1, which is 0. 0 plus 0, 0. So g of 0, 0. And guess what? Pi over 2, again, we get cosine of pi, which is minus 1, but the absolute value makes it 1. So we get log of 1 for the first term, and then plug in pi over 2 into the second thing, and you get, again, a log of 1, which is 0. So these are 0. And you can also prove that g of b is equal to g of pi over 2 minus b. Because this is 1/2 the natural log of the, well, it's probably better for me to not even, forget about the logs. Forget about the logs. Let's just focus on the inputs to the logs, all right? So like, what's the cosine of 2 times pi over 2 minus b? Well, that's cosine of pi minus 2b, right? Which is, by the way, cos pi cos minus 2b. Because the other term is 0 in the cosine addition formula, right? The other term is like a sine, but sine of pi is 0, so that's gone. But cosine of pi is minus 1. And so we get minus the cosine of 2b, or minus 2b if you prefer. And so, in other words, this and that match up after you hit it with absolute value, right? You can see that the first term in the antiderivative is going to match up at these two different boundaries. And likewise, the secant, if you work it out, well, again, secant 2t is 1 over cosine, so that's going to match up just the same. Well, actually, it's a little bit different. So what ends up happening with the secant of 2 times b minus 2 times pi over 2 minus b plus the tangent of 2 times pi over 2 minus b. So what you got is you've got a secant of pi minus b, or rather secant of pi minus 2b, and then plus the tangent of pi minus 2b. So what happens with that? The secant of pi minus 2b is really just minus the secant of 2b because it's the reciprocal of it's just from this cosine calculation that we already did. So this simplifies to minus the secant of 2b, and this simplifies, well, tangent is pi periodic. So you can drop the pi, and then sine is also odd, so you can pull out the minus, so we get minus tangent of 2b. And after you hit that with the absolute value function, you've got the same value for big G. So with my setup, the way it happens, when you work out all the details of each sub-quarter circle, the antiderivative is 0. It's 0 at the 4 regular points, the non-singular points. Theta equals 0, pi over 2, pi and 3 pi over 2. The big G is 0. And it's always the case that as you approach from the left and the right, or excuse me, from the counterclockwise and clockwise direction, you always get cancellation on each thing. So it works out, in fact, that this is 0. Yeah.
So when you did the limit, that was just for that first part of the integral at the top?
Yeah.
The part that you underlined. So would you have to do that for each piece?
Yeah.
Just doing it for one?
No, you have to do it differently for each piece, and I don't want to eat up all the class time. But I have kind of a yucky. So like here's the for this one I would approach b goes to 3 pi over 4, and I go pi over what's that, pi over, I can't even read my writing, pi over 2 to b, and then I go 3 pi over 2 minus b to pi for the other piece. And so I had to really think about it to set up these symmetric things, but I will scan and post this for you guys. It still might be simpler to do if you could think of a way of doing it all at once in some kind of symmetric fashion. I'm not opposed to that. Or plug it. Why, how would Mathematica even know what to do here?
Well, I had to set up all the limits. Like,
Oh.
I just do the calculus myself.
Oh, okay, okay. Now, here, let me show you another one that's much easier. So Kang had an idea, which is it might be interesting to look at the integral along the hyperbola. Along the hyperbola, like the unit hyperbola. Like what happens if this is the unit hyperbola, let's say C2, and you want to do integral along C2 of dz over z. What would that look like? Is that anything? And I was able to quickly prove, no, it's not anything. Because this one is easier. Like, what's the parameterization of the unit hyperbola in the hyperbolic plane? Well, it's cosh t plus j sinh t for t in the reals. In other words, that is, I would strongly encourage you not to write that. Instead, we should write z equals to, see, I haven't done enough of this with you guys. What's the, if you see cosine t plus I sine t, you immediately go, it's e to the it. What? So this is in fact e to the jt, right? And so dz, dt is, or let's say dz is j e to the jt dt. And so this is just the integral from minus infinity to infinity of j e to the jt dt over e to the jt, also known as j times the integral of dt from minus infinity to infinity, also known as 2j times infinity. In other words, it's not anything.
There's a question John and I were wondering about yesterday, because for the complex numbers and symbolic numbers, you have a simple formulation of exponential. Is that the case for all algebras?
Yes, any algebra I can formulate the exponential as the series. Exponential is generally defined just to be by the power series.
And then can you get a logarithm and then have the derivative be the reciprocal always?
Well, the problem of developing a logarithm over an algebra is more subtle. And we always face the trouble, if there's complex parts to the algebra, then there's always the ambiguity of the angle degeneracy for the complex components. But otherwise, you might be able to find, well, anyway, the exponential is not surjective. So we can only take the logarithm of something that's in the range of the exponential without some kind of funny business. And so the range of the exponential for this one, if you think about e to the I guess my question would be, what would be the range of the exponential?
We found that in the earlier mission.
E to the z. I have you guys do that? So e to the x plus jy, which was what? E to the x cosh y plus j sinh y. What's the... Oh, I had you find the range of that?
Yeah, we did from 48.
Oh, okay. But yeah, it's not everything, because it's just not everything. I know it's not everything. I mean, I know it can't be zero divisors, because as I showed you guys in abstract, we were doing this in abstract, I proved to them that the exponential takes on unit values. It can never hit the zero divisors. So what my expectation is that the range of the exponential is actually kind of in between these zero divisors. It's probably that quarter sector. And to hit the other parts of the hyperbolic plane, you have to multiply by j, or -1, or minus j. Sounds like something you've been doing. And that corresponds to Cooper-Ramsey's sort of 4-polar coordinate scheme, which I may or may not have showed you guys.
Yeah, but we pretty much tried it.
It's good. It's good. It's good.
Are you able to talk about problem 95 for a bit?
Yes, we can do that. So all I'm trying to get here, guys, is just a sample calculation. So remember, like, the foundational thing for Cauchy's integral formula is really that the integral of dz over z of the unit circle is 2 pi I, right? So if there was something analogous to the Cauchy's integral formula, it's hard to see how that could fly given this calculation. You know? Now, my brother has a sort of a more big picture dismissal of the hope for a Cauchy's integral formula. He says that the whole idea of Cauchy's integral formula and the residue calculus is based on isolated singularities, right? And our singularities, in other words, places where division's not defined, they're far from isolated here, right? There's a whole stupid line of them, right? These are not isolated singularities. There's a whole string of them. So any kind of Cauchy integral formula has to somehow combat that structure and find a way around it. And I don't know if it's possible or not. I'm not, it's hard to prove something can't be done, right? You can't really prove something can't be done. We've proved that the most naive notion of Cauchy's integral formula doesn't survive here, right? But there might be something, some natural analog. Now, Cauchy's, on the other hand, you could use this calculation to do more. Like the fact that we've calculated this as 0 allows us to say other integrals are 0, I think. Because we do have that. What other theorem do we know? What is it? The integral of f of z dz equals to what over the boundary of some region is 0, provided what? If it's holomorphic on D, right? With respect to the algebra differentiation, we still have that theorem, the Cauchy, what's that called? The Cauchy integral theorem, right? As opposed to Cauchy's integral formula. And so that allows you to do things like, if you can look at the D as being two things, right? Like maybe this part and that part. If this is C1 and this is C2, then you have things like the integral over C1 plus the integral over C2 is equal to 0 for f, right? And so if you could imagine other things like, I don't know, see, now I'm hesitant. I don't know, I feel like there might be a way to take this and get more from it using Cauchy's integral theorem. That would be something that I would try to investigate next. You know, using the idea of like deformation of the given result. See what I can get from that. Okay, you had a question about 95 that I keep stopping from answering. What was 95? Let me project it. See, the way I first looked at there not being a Cauchy integral formula, guys, for an arbitrary algebra is this. If your algebra is R cross R, right? and you have a function, which is really a pair of functions, f1 and f2, from a to a, and you have an a-differentiable function. What's that mean, to have an a-differentiable function on the direct product of R and R? It means that the Jacobian of f looks like this. Which is to say that f1 is equal to f1 of x, and f2 is equal to f2 of y. So the first component function just depends on x, the second component function just depends on y. In other words, a R cross R differentiable function is simply a pair of differentiable functions, f1 and f2. Oh no, this is just, well, that's, I was not, we could also talk about that, that's true, but the reason I'm just bringing this up at the moment is, curses. What are we on? We're on mission, what class am I in? 331, all right. Sorry, I don't have it open, I have to go back to the source. So you guys enjoying the contour integrals? They're kind of relaxing at this point, aren't they? In their way? No? Not 95? Oh, so you're asking me, oh man. I thought you were asking me about something interesting.
No, the interesting ones.
All right. So to finish my thought, Cauchy's integral formula relates differentiation and integration. It says that if you have one complex derivative, you have infinitely many, because of the Corsat theorem and all that. That gives us the continuity of the derivative necessarily. There is no such theorem for real differentiable functions. I can have a function which is once real differentiable but not 3 times differentiable, right? So there are functions which are a-differentiable here, which do not satisfy Cauchy's integral formula simply because they don't have that, you know, you can have real differentiable functions which are not infinitely real differentiable. But that feature is automatically necessary for a complex differentiable function. So you wanted this one, huh? So what's your question?
I think the big question is what function to analyze in the first place.
Ah.
We tried replacing flux, like replacing natural log with flux and theorem, and then did a bunch of stuff, and then like
People come to it.
found the limit of x log x as equals to 0, and then proved that everything works out, except that we get no information about the integral we want because log just has an additive periodicity rather than
Uh-huh. I will help. Just give me a second here. Right. It's log z over z squared plus b squared.
which log?
Appropriate choice of log. How about this? I don't know, what would that be? Log sub minus pi over 2 or something like that? I think if you look at that,
How would that be the problem? Because you end up, like what we end up with is you have the two integrals on those two sides are like natural log plus something and then natural log plus something else. So when you add them, and then they're like negatives of each other. So when you add them together, the natural logs cancel.
no. Not when you take the branch cut there. You'll get different arguments. You have different angles on the,
Yeah, you have different angles, but the natural log part cancels.
Yeah, because you have, in the other examples where we use the pupil contour, there's a multiplication from the argument
since we're out of time. You've driven me to it. Come on. Let's see here. It is additive, that's true. But, well, the thing is, these go together to give you the integral of the log.
No, for us, one was plus and one was minus.
Yeah.
Is it different here because you're doing
Oh,
integrating in opposite direction? Sure.
I gotta stop, but yeah. So I'm not sure what to tell you, but this is how I did it.
So we're just going to be a copy of this exact thing.